and Jasper will be giving the talk.
Thank you for the introduction. I'm glad to be able to introduce today one of our recent works on structure-aware private set intersection. It's a joint work at Oregon State University with my co-authors Mike and Gayatri. I'm sure most of you are familiar with the standard private set intersection problem. You have two parties, Alice and Bob, and they both have a set of discrete points, and they're interested in learning the set of items that are common to both these sets. And you have an additional privacy constraint that no party should learn anything other than the expected output. So for example, Bob should not learn any of Alice's items outside the common elements. So this problem has been well studied in the literature. So I'll be interested in a variant of this problem. So let's say Alice and Bob are visiting Santa Barbara to attend crypto for a week, and they visit a number of places in and around Santa Barbara. And at the end of the stay, they're interested in learning if they had been to any same locations in the city. So it's unlikely to be the case that they would have stored the exact same GPS locations for each place they visited. So what we would need is some sort of a fuzzy PSI protocol where we want to find points of Alice and Bob, which are within some distance delta in some metric space. So one trivial or a naive way to do this would be to redefine Alice's set as all the points within a delta radius ball for each of its original GPS coordinates. And then we run a plain PSI protocol between Alice's expanded set and Bob's discrete points. While that does solve the fuzzy PSI problem, it isn't the most efficient way to do this. Because for any traditional PSI protocol, the communication complexity is proportional to the input party sets. So in this case, it will be proportional to the expanded set of Alice, which can be considerably larger than the set of original discrete points. However, you note that here you have a structure given over one of the party's input sets. What Alice holds is delta radius balls, which are delta radius balls in some metric space. So the question is, could you sort of exploit that advantage to get a more efficient PSI? So in this work, we introduce a new framework for private set intersection, which gives a very practical way to solve the fuzzy PSI problem that I mentioned earlier. And it's in fact a lot more general. You can actually employ it for doing PSI, where one of the parties has any arbitrary given structure and not just a union of balls. So in our framework, we reduce the problem of private set intersection to a new variant of function secret sharing, which we term as weak FSS. And we end up reducing the communication complexity of the protocol to be proportional to the FSS share size of the structured set. So I'll get to this detail later, but for now you can think of it as the description size of the structured set, which in this case would be the center of all the balls.
Sorry to jump in. Apparently the slides are not visible right now during Zoom over Zoom.
Oh.
Is there maybe from the IT team?
Yeah, I can screen share. I'm not sure how to go full screen in this.
I believe it's the arrows that are pointing away from each other, the diagonal arrows.
Oh, thank you.
Thank you so much.
So as I was saying, we reduce the problem of PSI to a variant of FSS. And furthermore, we introduce new FSS techniques where we sort of exploit this new weak FSS definition to give sort of very efficient secret sharing schemes for union of geometric balls. So almost all the PSI protocols that we are aware of is based on this OPRF paradigm that I'll introduce soon. And our protocol is sort of based on this paradigm as well. So in this case, you have two parties who want to compute the private set intersection. And you run an OPRF protocol, which takes as input Alice's discrete set. And the OPRF protocol outputs a random function to Bob, and it outputs the evaluation of the function on Alice's input points back to Alice. And this protocol leaks nothing but the expected output. So Alice does not learn the function f, and Bob does not learn any of the input points of Alice. And essentially now Bob can compute this random function f on its inputs y1, y2, and so on, and send it to Alice. And Alice can use that to compute the intersection. And for any typical OPRF construction that you can use here, the communication complexity is always proportional to the size of Alice's set. Our goal would be to design a structure-aware OPRF where the communication of this OPRF protocol is instead proportional to something like the description size of X instead of just its cardinality. So this is how the main protocol would be structured. So given a weak FSS construction for the structured set of share size sigma, you can actually design a structure-aware OPRF which has communication proportional to lambda times sigma, where lambda is the security parameter. And that gives you a PSI protocol as well with communication that's proportional to sigma. We did look at the OPRF paradigm. So for the rest of the talk, or at least the next few slides, I'll essentially focus on how you can exploit this weak FSS, which I'll define next, to get a structure-aware OPRF. So next we'll define Boolean function secret sharing. It has two functions. Firstly, a share function, which takes as input a set, and it outputs two keys, which secret share the set A. So you want each key to hide the input set A, or they should look uniformly at random individually. And the eval function is such that whenever your input X is in the set A, you want the evaluation of both the red and the blue keys on the input X to be equal. Or in other words, their XOR should be 0. And when X is not in A, you want the evaluations to output different bits on both the keys. You could have actually inverted 0 and 1 as well, and the entire protocol would still work, but it just helps present the protocol in a more simpler way. And for someone who's familiar with FSS, this may seem a little jarring because usually you secret share functions and not sets. But you can redefine this in the original framework as well, where the function is the set membership function of the set A. But for simplicity, we'll stick to this syntax. So now let's see how we can use a function secret sharing scheme for a structured set to give an OPRF. So firstly, Alice takes its structured set and it runs the share function multiple times, specifically 128 times in a protocol, and it generates pair of FSS keys. And then we'll run the oblivious transfer protocol, using which essentially Bob can obliviously select one of the keys from each pair at random. So S has this selection random vector S, using which it selects one of the shares from each pair. And we define the OPRF function as follows. So Bob can essentially, given an input X, Bob can essentially run the eval function on the input X, given all of its keys that it received from the OT protocol, and concatenate those. And on the left-hand side, you see the shorthand notation for the concatenation of all the evaluations. And then you can apply a random oracle on top of that, and that will define as f of X. So Bob can compute f of X on any input X. Now let's sort of try to analyze for which inputs X can Alice identify f of X. So when X is in A, we know that the evaluation of the red and blue keys on the input X are the same. Hence, in this case, actually, you could have computed f of X by actually running evaluation on just the blue keys, all of which are known to Alice, and Alice can essentially compute f of X when X is in the set A. This is where the clean notation sort of helps. And notice when X is not in A, we know that the evaluation of the red and blue keys on the input X would be different. Hence, in this case, if you try to work out what f of X would be, it turns out to be the evaluation of all the blue keys on the input X, XORed with this random bit vector S that's only known to Bob. And that sort of gives you sufficient entropy in the input of this random oracle, such that Alice will not be able to identify this OPRF output, or in other words, this would look completely random. So that gives the needed security for the OPRF. Now, if you'll notice, actually looking at this framework, we sort of noticed that we could actually relax the FSS definition in a couple of ways, and the protocol would still work. So that's what we sort of define as weak Boolean function secret sharing, which is parameterized by P and K. And I'll refer to the original definition as strong FSS to just sort of differentiate between both of them. So the first relaxation is we allow the evaluation to output multiple bits instead of just one. So when X is in A, again, you want the evaluation of the red and blue keys on the input X to be equal. And in the case when X is not equal to A, is not in A, you want the evaluation of red and blue keys to be just unequal, or their XOR should not be 0 to the K. And secondly, we allow for false positives. What I mean by that in this context is when X is not in A, we allow for some chance for the evaluations to even be equal. So all we want is the evaluation of red and blue keys on input X to be different with at least some probability P. It need not be always true. So the first change is actually, it's easy to see how that would affect the OPRF protocol, and the protocol would still work. I'll essentially in my talk focus on showing how the false positive probability would affect our OPRF protocol. So yeah, we'll sort of just look at the security of the OPRF protocol and just see how Alice would not be able to identify an element, would not be able to compute f of x when x is not in A. So in the strong FSS variant, this is how it f of x looks like for x not in A, and due to the random bit vector s, f of x looks completely random. In the weak FSS case, let's take the example where p is equal to half. So in this case, instead of 128 pair of FSS keys, I'll essentially run the OT protocol 440 times. And the reason is running the OT protocol 440 times ensures me that with a very high probability, at least 128 pair of those keys would satisfy this strong FSS definition, which in this context means that the red and the blue keys would evaluate to different bits. So if you sort of try to rewrite f of x again in this sort of in this framework, you essentially end up with evaluation of all the blue keys XORed by the 440-bit string, which has at least 128 bits of entropy. And that is sufficient to give you the OPRF security. So there's a trade-off here. We allow for a false positive, and we ended up increasing the number of OTs. So there's this sort of trade-off that is introduced in a protocol. But that's the gist of the construction, essentially. So once we sort of came up with this framework, we noticed that although we're interested in just structured sets, we noticed that this sort of FSS and weak FSS techniques are sort of present in previous PSI constructions as well, although almost implicitly. So just to give you one example. Before that, so this is sort of what the framework sort of looks like. You plug in a strong or a weak FSS into our OPRF framework, and you end up with a PSI protocol. So I'll show you an example of a weak FSS, which sort of gives you one of the previous PSI protocols. So this is a weak FSS for an arbitrary set based on Bloom filters. So you have a set A, and you want to sort of construct weak FSS for that. So you have a unit vector, which will be your Bloom filter, and you will essentially have 0 in here, which sort of represents set membership. So to insert an element foo into this Bloom filter, you essentially hash the element foo and make the corresponding bit 0. It's a single hash Bloom filter, which is really bad, but we'll do with that for now. So similarly, if you look at bar, you can hash that and make the corresponding bit 0 as well. So you prepare this Bloom filter for your set A, and then you prepare your FSS keys as just XOR sharings, random XOR sharings of this Bloom filter. So in this case, notice if you want to evaluate these FSS keys on some input foo, let's say, which is from the set, you essentially query the FSS keys at hash of foo, and that will be your evaluation output of the FSS. And notice that in this case, since foo is from the set, the XOR of the corresponding FSS entries would give you 0, which is what we need. But it's a really bad Bloom filter. We are just using a single hash function. So it could happen that sometimes you query an element outside the set, and it could still give you a 0 as the output of the XOR of the evaluations. But that is okay, because in the Bloom filter, you can actually bound the false positive probability, and that actually corresponds exactly to the weak FSS false positive probability. And what's sort of interesting is, if you plug in this weak FSS into our OPRA framework, you end up getting Chase Meow Crypto 2020 PSA protocol, which was sort of interesting for us because in their original work, they don't sort of explicitly mention Bloom filters, and there is this sort of hidden FSS in it. And it's not just their work. There are a number of other PSA protocols which has this implicit weak and strong FSS. So you can look at IKNP from the lens of a strong FSS as well. So if you do an IKNP-based PSA protocol, there's actually a strong FSS hidden within it. Another protocol example is SparseOT from Crypto 2019. So in that as well, there is an weak FSS based on polynomials, which when plugged into a protocol, essentially gives you the SparseOT protocol. So we sort of noticed that for a lot of unstructured set-based PSA protocols as well, our sort of framework sort of generalizes all of them. But what we are interested in today is looking at structured sets. Can we design efficient weak FSS for structured sets? And specifically, we are interested in union of balls, where a ball could look something like this in an L2 norm. But if you use a different metric space, it could look really different. So this is an L1 ball in 2 dimensions, and this is an L infinity ball. And these are the easier geometric objects we can deal with using function secret sharing. So we'll stick to this for the rest of the talk. And L infinity is nothing but just an intersection of D intervals. So those are sort of easier objects to deal with. But all the ideas that I discuss will extend to L1 norm as well, which is an intersection of each L1 ball is an intersection of 2 to the D-1 intervals, which is exponentially worse, but the ideas would still extend to L1 norm as well. So before I introduce our weak FSS constructions, let's see what can strong FSS give us from previous work. So if you look at any L infinity ball, it's an intersection of intervals. And for intersection of intervals, there's a decision tree based FSS, which can be used in the work by Boyle, Gilboa, and Desai. And they get FSS key size, which is proportional to B to the D, where B is the number of bits in any coordinate of an input in the domain. But essentially, the key point here is it's exponential in the number of dimensions. So it's not as efficient. And that's how you sort of get an FSS for a single ball. And for a union of balls, the idea is given a point, you can run the FSS eval on each of the balls and then add them up. And there's some technique works in the case when the balls are disjoint. And that essentially ends up increasing your FSS share size by the number of balls and the eval cost by the number of balls as well, since you need to run the eval for each point, for each ball given a point. So I'll show an improvement over both of these cases in the weak FSS scenario, where we sort of use the relaxation of the weak FSS to design a more efficient FSS. So we introduce a number of weak FSS techniques, which build on top of one another and also known strong FSS techniques. So this is just a flowchart of all the ideas in our work, but I'll focus on 2 ideas in this talk today. And we believe that we have barely sort of scratched the surface in terms of exploring, in sort of exploiting these weak FSS relaxations to designing efficient secret sharing. But the general theme that we've noticed is that this sort of weak relaxation will give us more efficient function secret sharing, which I'll show you next. So one of the techniques, which is really simple, but it'll turn out to be really powerful, is the concat technique, where given function secret sharing scheme for 2 sets A and B, our aim is to get a function secret sharing scheme for the intersection. So let's say you can secret share 2 sets A and B, and you have the corresponding pair of keys. And the question is, how do you get function secret sharing scheme for the intersection? And here we exploit the relaxation that you can have multiple bits as the output of the eval. So the very straightforward idea of just concatenating the evals and treating that as the evaluation of the intersection. So now notice an element X is in the intersection of A and B only if the evaluations XOR to the bit string 0, 0. And in this case, the shared size of A intersection B is just you having the two keys for the sets A and B. So that's really efficient. And specifically, as I mentioned, an L infinity ball is nothing but an intersection of D intervals. So you can just concatenate the FSS for the D intervals that actually give you an FSS scheme with share size that's proportional to the dimension. Instead of having it being proportional to X something B to the D, which is exponential in D. So that's a great saving. So very simple technique, but it does help reduce the share size. Another technique we introduce is spatial hashing, where we sort of try to reduce the share size and the eval cost when sort of trying to handle a union of balls. For this talk, I'll just sort of focus on the eval time. I'll try to show how you reduce the eval time from a multiplicative factor of n. So the idea is you overlay a grid structure on top of these L infinity balls, where each grid cell is an L infinity ball as well of the same radius. And then you essentially mark the cells which intersect with an input ball. We call those active cells. So that's the shaded region in this figure. So our goal would be to make sure that the FSS gives the correct output within the shaded region. That's the region sort of we care about. So the idea is for each grid cell, for each active grid cell, we will prepare grid FSS keys that sort of give correct output within the grid. And if I go a step back, notice how within each grid cell, at max, a constant number of balls would intersect. In the 2-dimension case, it would be 4. So you can prepare each grid FSS by just preparing 4 FSS keys. And that would be your grid FSS. And your FSS keys for the union of balls would be 2 polynomials, which given a grid FSS ID, it should output the corresponding FSS for the grid. So this is what if we sort of interpolate the 2 polynomials on. Now notice when an input X is within a grid cell, within an active grid cell, this polynomials would output the correct grid FSS, and that would give the correct output. But what about the case if you try to evaluate this FSS on a point in the non-shaded region? So in that case, your polynomials would end up outputting random pair of strings. And here we exploit the fact that we allow for false positives. So in that case, our FSS would output random bits, but we are okay with that because we allow for false positives. So we sort of really care only about the shaded region. And notice how we reduce the eval cost from n to just 4 in this case, because to evaluate a point, you just need to evaluate on input blocks, which are intersecting with the current grid cell. So just to sort of give you an overview of our FSS costs. So in the strong FSS case from previous literature, you had share size, which is exponential in dimension, and you had eval cost, which was n times the eval cost of a single ball. So we ended up reducing the eval cost to 2 to the D. I just looked at the 2 dimensions, but if you try to generalize it, you actually get a factor of 2 to the D. And we reduce the exponent of D as well in share size. While I did not sort of discuss all the constructions, we sort of ended up reducing the share size even more and even the eval cost by assuming a stricter geometry over the input balls, like assuming they are very sort of far apart relatively. And the overarching theme in our constructions was that we can exploit this weak FSS relaxations, and we can exploit a stricter geometry over the input balls to get a more efficient FSS. To summarize our results, given a function secret sharing scheme of size sigma for any structured set, you can get an OPRF protocol or a PSA protocol where the communication complexity is proportional to sigma. And we give a lot of simple yet powerful weak FSS techniques, which sort of helps us handle, helps us optimize the FSS for union of balls. We believe we have sort of barely scratched the surface in terms of exploring structure-aware private set intersection, and there's a lot left to be explored for anyone interested. So for sort of one of the key questions is, can we make the computation sublinear? So while we sort of focus on the communication in this work, we try to make that sublinear in the size of the structured set. If you sort of closely inspect the protocol, our computation for Alice is still sort of linear in the size of the structured set. We exploit the structure in one of the party set. Could we also assume some structure in the other party set and sort of exploit that? So that's another question. Again, our framework is restricted to semi-honest. There are some challenges if you try to sort of translate it into the malicious setting. As you would have noticed, all the share size that I showed, most of them had an exponential dependence on dimension. So they don't really scale very well in higher dimensions. And it's even worse for L1 metric. So yeah, can you sort of improve on the share size as well? Finally, we were inspired by the fuzzy PSI problem. So we just looked at union of balls, but you can sort of apply this framework on any arbitrary structured set. So there's a lot left to be explored in that sense. Thank you. And our paper is on ePrints, and we just made our implementation public as well.
Since we're running a bit behind schedule, we can take maybe one quick question while the next speaker slides get set up. Is there anything? I'll jump in for a quick one then actually. So what's the best weak FSS for L2 balls, for example?
I didn't have a slide for that. Okay, so essentially what you can do is, we can't do exact L2 balls, so that's not known, but you can approximate an L2 ball by a polyhedron.
Okay.
And depending on how many sides you want on the polyhedron, that increases your FSS complexity. But at the same time, you get a closer approximation to L2. So yeah, L2 is sort of still something that we need to explore in more detail. Yeah.
Interesting. All right, let's thank the speaker again. The next talk will be on two-round MPC with round collapsing revisited toward efficient malicious protocols. This is the work of Rachel Lin and Tianren Liu, and Tianren will be giving the talk virtually.
Oh, thanks for the introduction. Does the audio works now? Hello?
Yes, we do hear you.
Okay, cool, thank you. Yeah, welcome to my talk. Today I will share, oh, I also open the camera. Today I will share our recent work about the simple and efficient two-round MPC construction. I'm Tianren Liu, recently joined Peking University. Unfortunately, I cannot join you in person. My co-author is Rachel Lin from the University of Washington. She will join you in person there. So you all know MPC. There are N parties. Each has its own input. They talk and jointly compute a function. For security, any adversary, even if he corrupts many parties, should learn nothing beyond the function output. Okay. So using MPC in the real world can be very expensive for many reasons. Typically, network is the bottleneck, measured by the communication complexity. Latency is also a big issue. So right now, when I'm talking to you, there's a network delay about 1 second. So if you and I run a protocol of a few thousand rounds, it will take an hour. Round complexity likely to be the bottleneck, especially for computing small functions. And we know MPC protocols need at least 2 rounds. Okay. Moreover, we also want to ensure that the communication complexity doesn't blow up too much. Okay, so here's our setting. We stick to 2-round protocols. The adversary is malicious and corrupts any number of parties. In this setting, there are already many previous works. They belong to a few approaches. Okay, so for example, you can start with a passive secure 2-round protocol and use NISC to enforce on its execution. Or you can use the so-called round collapsing technique. I won't go into the detail, but roughly speaking, you start with a multi-round protocol. Then somehow in 2 rounds, every party can compute the gobble circuits of all the next message functions of the multi-round protocol. And recently, there's also work on doing two-round MPC using the MPC in the head. Okay. So for two-round malicious protocols, there are many works in the literature, and I can only list a few of them in this page. The existing protocols are not very efficient. Some use very expensive assumptions such as I/O or FHE, and some because they make non-black box use of assumptions. For example, say there's a cryptography function. In the protocol, I prove to you that I evaluate the function correctly using this. Or say, I use the double circuit of this cryptography function. Such operations are known to be highly inefficient. Among the previous work, there are two exceptions, JIS and IKSS. They didn't make non-black box use of assumptions, but their technique in some sense make non-black box use of some other MPC protocols. And the other conversion increased the complexity. At least to me, their protocol seems very complicated. In this work, we aim for an efficient MPC protocol that is also conceptually simple. All techniques are quite elementary, and we make black box use of the assumptions. Okay. So the model of our protocol, we assume correlated randomness is distributed between every pairs of parties before the protocol starts. So one party receives A1, B1, the other receives A2, B2, such that A1 times B2 equals B1 plus B2. So this correlated randomness is widely used and can be efficiently generated and stored because there's the so-called pseudo-random correlation generator. So parties only need to store some correlated seed, and later in the protocol, they can generate correlated pseudo-randomness on demand. We also assume PRG, random oracle, and broadcast channel. The security notion is security with a board against static assumption. So concretely, the communication complexity of our protocol is the circuit size times security parameter times NQ. As you can see, I didn't write an exact number for the complexity of this protocol for a few reasons. So one, they look more like feasibility results. The comparison might be unfair. Also, they convert one MPC protocol to another. For example, JIS started with a multi-round protocol and converted to two-round, but they didn't enforce which protocol to start with. Therefore, it's unclear what's the complexity of the ending protocol. And finally, despite what starting protocol you choose, their conversion steps introduce too much blow-up, so our protocol is still more efficient. But in the literature, we also have even more efficient protocol in the constant round setting and the many round setting. I guess it's a big open problem to say whether how the round complexity related to the communication complexity. Okay, now I go to the technical part. First, I gave the high-level idea of our protocol. The most important idea, also the framework, is called multi-party randomized encoding, introduced by Applebaum, Brusky, and Saburi. So, say you want to construct MPC computing function f. MPRE allows you to reduce the tests to build to construct MPC for another function. So how it works? So every party locally preprocesses their input, and then they call the function f hat. And after they learn the output of f hat, they locally decode it. Okay. So as you can see, only the middle part calling f hat is interactive. All the other step is non-interactive. And this is reduce our work from, if you want to build a two-round protocol for F, it's so fast to construct the MPRE for F, and then construct two-round protocol for compute the F hat function. Throughout this talk, we restrict the F hat function to be a degree 2 function. So when ABT start to consider this problem, they consider this in the honest majority setting. In a previous work with Lin and V, we started we generate this framework to the honest minority setting, and in this work we go to the malicious and honest minority setting. So this is the MPRE. In LLW, when we generalize this framework to the honest minority setting, we also require the use of correlated randomness. So the preprocessing function has the correlated randomness as part of the input. So is the MPC function for computing the degree 2 F hat. And the communication complexity is circuit size times preparameter times input already. In this work, we consider malicious parties. So there are few bad things might happen. The malicious party can cheat. One thing is like, although the malicious party receives correlated randomness, he might fit something else in the preprocessing function. Second, the malicious party might just compute the preprocessing function incorrectly. And finally, we also need to upgrade the MPC protocol from semi-malicious to semi-honest to malicious. And in the rest of this talk, I will briefly go through how we deal with this challenge. We also, to fix these vulnerabilities, we also need to make sure the blowup is small so that our communication capacity is the same as the previous semi-honest protocol. So the first one, we want to ensure that the malicious party use the right correlated randomness. Of course, if you think of it, there's nothing can stop the malicious party from using wrong correlated randomness. The only thing we can hope for is like we can hide the privacy information of honest party when the malicious party make a malicious move. When the malicious party fits something wrong in the protocol. So here is our first attempt. Say one party want to hide his privacy information. He samples randomness R and let the F hat function output the following message. This message perfectly hides the information when there's a malicious move. But the problem is that this function is a degree 3 function. And as we said, the F hat function has to be a degree 2 function for the later part 2. So we make a different attempt. So observe that when there is a malicious move, this matrix is full rank, if and only if. So therefore, if you want to, honest party want to hide his private information, he can sample more randomness and output that matrix time the randomness plus use that to one-time pad the information. It's obvious that when there's a malicious move, the information is perfectly hidden. But here A1, A2, it's leaked, which is undesired. Now, with all this observation in mind, we present our actual construction. So first step, we need to replace the scalar version of the OLE correlation into the matrix version. So now A1, A2 becomes vectors, and B1, B2 become active secret sharing of A1 tensor A2. Okay. Now, if you want to hide some information, you first pick two random vectors. And due to the randomness, you can show that this matrix is full rank if and only if there's a malicious move. Okay. Then the rest is similar. I sample more randomness. I ask F hat to output that matrix times my new randomness plus my private information. Okay. For the degree, note that because V1, V2, and R1, R2 are all known by one party, that party can locally multiply them. And therefore, the F hat output an effectively degree 2 function. For privacy, there are some leakage, but because we have replaced from the correlated randomness from the scalar version to vector version, we have A1 is much longer. So what all we need is some coordinate of A1 is unleaked. So this kind of leakage is fine. As you might observed, like things in these slides doesn't look so secure, and that's right. This is just the main idea, and it can be formalized. Also, for efficiency, like this slide also looks it would bring like n-squared blowup, but actually it didn't. So for the next one, we want to ensure that the malicious party compute the preprocessing function honestly. How do we achieve that? Okay, we just postponed the problem to the next slides. So we just say, okay, later when we construct the two-round MPC for computing F hat, that MPC also ensure the input is well formed. Okay. And therefore we call our MPRE semi-malicious because the MPRE itself doesn't enforce the preprocessing function to be evaluated correctly. The duty is strict to the MPC part. Okay. Finally, how would we construct two-round MPC for F hat? The important observation is that the semi-honest MPC for computing F hat in LW, it's already somewhat maliciously secure. Okay, I will just briefly recap that. Without loss of generality, in the semi-honest case, you can assume F hat is just x1, x2 plus z1, z2, where x1, z1 held by one party, x2, z2 held by the other. Okay. So the protocol uses correlated randomness. In the first round, okay, this is the protocol. You don't need to verify it works well. And it's malicious secure. Okay, it actually satisfies a weaker notion of security. We call it security with output substitution. It's very similar to the privacy with knowledge of output security. And it can be lifted to the standard notion of security with support. Okay. And in the first round, note that the message C1, C2, they can be viewed as commitment of two parties input, X1 and X2. And they can also, the input can be easily simulated. But when you go to the malicious setting, you can no more assume the function is that simple. But still, without loss of generality, you can assume that the F hat has a long output, but each bit of the output looks like x1, x2 plus z1, z2. Okay. So for example, you can say another bit of the output is x2, x3 plus z2, z3. And we use the same protocol for computing it. What could go wrong here? It's like when you simulate this protocol, you simulate x1, you simulate x2 from the left-hand side of protocol, and you simulate x2 from the right-hand side protocol as well. In the similarity case, it's fine, but in the malicious case, maybe these two x2 are different. Okay. So therefore, we need a way to for every party to prove that okay, I fit consistent x2 into different extraction. How would we do that? Similarly, in the first step, we need to replace the scalar version of the correlated randomness to the matrix version of correlated randomness. And now, because A is longer, in the first round, we can send a commitment of a longer message. So we can send x2 paired with something else. Okay. Although I won't show in this talk, so such kind of commitment. So if you use OLE correlation to commit message, it has a very nice property that it allows you to partially open the commitment. So for example, the other party can send a vector Q, and then this commitment, you can open the commitment, you can open Q inner product, what's the message behind this commitment. So we just use this property in the other side as well. Okay. So in this way, because Q1 and a Q is randomly chosen by honest party, this enforces the potentially malicious party to commit the same message, otherwise it will be called. The problem here is that this check takes 3 rounds. So we use the standard Fisher-Shamir type to convert it into only 1 round. For Fisher-Shamir, we require random walk. Okay. So as mentioned, to prove consistency, we use a matrix version of the crazy randomness. We use the idea that this commitment can be partially opened, and we use Fisher-Shamir. We also need to have well-formedness. For well-formedness, actually it's not covered in this talk, but the idea is very simple. You only need to combine the above idea plus the idea of linear proof. So that's the basically construction. We make the MPRE semi-malicious secure, and we also make the MPC for computing degree 2 function not only maliciously secure, but also check well-formedness. And combining them gives you a 2-round MPC for computing any functions. Okay. So this is the overview of the talk. As mentioned, our complexity is circuit size times circuit parameters times n2. We also have another result for arithmetic branching program. It is secure, and it only makes black box access to the field. And our protocol is, because it only uses very simple tricks, so the computation complexity is roughly the same as the computation complexity. And that's it. Thank you for listening.
Again, we can take a quick question while the next speaker is setting up. Maybe just a brief meta question, to Tiernan. Do you have any thoughts about whether, how far the communication complexity could be pushed? For example, n squared or even beyond?
Okay. Well, yeah, we definitely try to push it to n squared, but we failed. Okay, so maybe the compression one. Yeah. So of course, that's the most obvious open question for our work.
Mystery then for you guys to solve. So let's switch to the final talk then. Final talk will be on more efficient, dishonest majority secure computation over Z2 to the K via Galois rings. This is a joint work of Daniel Escudero, Xiaoping Xing, and Chen Yuan, and Daniel will be the speaker.
Hello? Yeah? Okay, good. You have to full screen.
Yes, thank you. So I'm going to be presenting from my iPad, which is, you will apologize the toolbar and so on. So thank you so much, Elias, for the introduction. I'm happy to be here finally after some years of virtual conferences. And this is going to be another talk on MPC. More concretely, MPC over this ring that I'm going to explain right now in a moment. Right. So let's get started with a super quick introduction. So the setting, let's start with the setting. We're going to have n parties that I'm calling P1 up to Pn, and they're going to have private inputs, x1 up to xn. And the goal is that they wish to compute certain function that I'm denoting by f, and they don't want to use any trusted party. That's the standard setting when we consider secure multi-party computation. And the adversarial or the attack that we want to consider here, we want to consider an adversary that actively corrupt n-1 out of the n parties. So we call this also dishonest majority, because this is in contrast to honest majority when the adversary only corrupts, well, a minority of the parties. And we want that even in that case, the input of the remaining honest party, there is only one honest party, is kept private. So the keywords here are dishonest majority and active corruption. Active corruption is not the case where the corrupt parties deviate arbitrarily from the protocol specification. Right? So usually the function f that we want to compute, it's quite common to represent it as an arithmetic circuit over a certain finite ring. Arithmetic circuit being simply a combination of multiplications and additions over said ring. And what are the typical choices we care about when we want to do a computation? We typically choose a ring of this form. We choose Zm, which is the integers modulo some other integer m. And the reasons why we usually do this is because, well, there are several reasons, but if you choose m to be large enough, you can basically emulate integer arithmetic. If you want to do sums, if you want to do products over the integers, you can just compute an upper bound on the integers and then choose a modulus that is large enough. And the other reason is that if you choose m equal to 2, you can get essentially binary computation. So it's like Boolean arithmetic, Boolean circuits that, of course, have a lot of applications. So it's very common to use this type of rings for MPC. And finite fields, which is what you get if you choose m to be a prime, are actually quite common in MPCs because they are good for protocol design. And the most important property that we usually use is that every non-zero element turns out to be invertible. That's what defines a field. And this property turns out to be essential in building protocols. At least in a lot of actively secure protocols, this turns out to be an important property. Right, so an alternative that we've seen in recent years that may have certain advantages is not taking a prime, but taking a power of 2. By the way, I want to say that almost everything I will say during all this talk extends naturally if the prime is not 2p. But the case I want to make more emphasis on is 2. So it has certain advantages, and some of them we have verified experimentally in some previous work in SMP. And basically, the motivation is that if you choose k to be, for example, 32 or 64, you can get a reduction this model like for free in standard computer architecture. So that's a motivation. And also, it turns out that C2 to the k is in a way more compatible with binary computation, which is very good when it comes to doing what we call mixed computation. Sometimes you don't want to stay in the arithmetic world, you want to jump back and forth between arithmetic and Boolean. And these rings turn out to be useful for this type of settings. So that's very good. But unfortunately, this ring has a lot of disadvantages with respect to fields, specifically when it comes to protocol design. And they mostly come from the fact that there are many non-invertible elements. And in particular, there are 0 divisors. So you can see that this equation holds in this ring. This is 2 to the k, which is 0 in this ring. So this indeed brings some complications to the table when you want to design protocols over this ring. And we can see that we have like a massive line of works in the direction of doing dishonest majority MPC over finite fields. I'm just listing some some of them, and all of them basically follow a similar structure. They use additive secret sharing. By the way, I'm talking mostly about secret sharing based protocols. Of course, there are protocols you can base on homomorphic encryption or garbled circuits. I'm not considering those for the discussion. So they all use additive secret sharing with message authentication codes to prevent cheating. And the online phase, in fact, in all of them look pretty much the same. It's very similar. And for multiplication, they use multiplication triples. So they use these max, and these max, they tend to work only over fields because they require certain invertibility, as I was mentioning. And if you want to extend those works to operate over the ring C2 to the K, we have a different line of works that use slightly different techniques. So back in 2018, we introduced this work that proposed an alternative MAC mechanism, an alternative message authentication code, and then several works afterwards built on top of these to improve the communication complexity, mostly in the pre-processing. And they all use this idea, which involves working over a larger ring. So in these protocols, we have to move to not an extension ring, but a larger ring, where you take the K bits you have and you have to add S bits on top, where S is going to be the security parameter. So you have an inherent overhead when working with this protocol. Right, and we're talking about computation modulo 2 to the K. Well, K equal to 1 is a particular case. So the case of binary computation. And you have some protocols that are specifically designed for this setting. I'm just listing some. And I think this one in particular will be important for our discussion because it turns out that a protocol will also apply for K equal to 1. We will also be able to improve this recent protocol by Cascudo and Gunderson. Right. And of course, I want to highlight that most field-based protocols already also work over F2 because that's a particular field. Right, so there is a lot of work in this direction. Again, MPC, dishonest majority over rings. And this is exactly where our work fits into. So let me tell you briefly about what this work is about. So we present yet another dishonest majority MPC protocol over this ring. And the features of our protocol is that it has a good communication trade-offs with respect to previous works. So I say good communication trade-offs and not just better communication because not in all settings we achieve better communication. Asymptotically we do, but depending on the constants, sometimes we don't, but like I'm going to discuss this in a moment. And there are three main technical insights, I will say, in this work. So there is this concept of Galois rings, which I'm going to explain later. They pop up in honest majority MPC a lot, and this is the first time we use it in the dishonest majority scenario. And there is also the concept of reverse multiplication friendly embeddings, or RMFEs, which again have popped up a lot in honest majority, and like this is also the first time we use them in the dishonest majority to explore their benefits. And I'm mentioning that we don't require certain re-encoding rounds, so we use them in a clever way with respect to previous work, in a more clever way that allows us to get better performance. Won't be able to discuss the details of that, but like I just wanted to highlight. And then finally, I think this is particularly relevant. So there are reverse multiplication friendly embeddings, which are the RMFEs. But prior to RMFEs, there were the MFEs, which are, well, non-reverse ones. I'm going to explain the difference later. And they actually weren't used in MPC so much. We do use them. We find an application for them to instantiate oblivious linear evaluation over ring extensions. So typically OLE is instantiated over integers modulo 2, which is OT, or integers modulo prime, or integers modulo 2k, but not over extensions, so polynomials. So we show an application of MFEs that allow us to get OLE over ring extensions while using OLE over the base ring with a communication complexity or with a number of poles to the underlying OLE functionality that is not quadratic in the extension degree. I'm going to get to that in a moment. Right, so I also want to mention that our protocol, unlike the prior splits to K and derivatives, also works for K equal to 1. Not all works do this, like for example, splits to K does not, because the preprocessing requires K to be at least a security parameter, which is fine for several use cases, K equal to 64 or K equal to 128. But our work also enables the case of K equal to 1, And moreover, as I will discuss in a moment, our protocol is general. It's like 2 to k for any k. And we improve over protocols that are specifically designed for the case of a k equals to 1. So let's discuss a little bit the communication complexity. This big table I'm showing here, all the communications are divided by n times n minus 1. All of them share the same factor. So let's discuss it. Let's remove this for now. It's the offline phase that I'm discussing here. So let me guide you a little bit. So we see two things I want to show you here. First, our constants are large. And this is something that may impact your eye a bit. But the interesting thing, at least asymptotically, is that our offline phase with respect to that of speeds to k doesn't have an overhead in the security parameter s. So our offline phase is independent of the security parameter. And if we instantiate, for example, with s equal to 64, well, we get this expression. So by the way, you can see that our constant here lowered from 8,000 to 5,000. I'm going to explain why later. It's because this is the worst case constant you can choose, but in some concrete cases, like s equal to 64, it turns out we can improve the constant. And in this case, if you choose, for example, k equal to 32, and you do the math here, it turns out that our protocol will use around 3/4 the communication of speeds to k. And asymptotically, if the security parameter increases, our improvement will be better. So that's what I'm saying. Asymptotically, we have an improvement. And for concrete constants, it depends, well, on your particular scenario. And for the case of k equal to 1, where we have this work by Cascudo and Gundersen, their offline phase has this number of bits in communication. L is certain parameter that I won't get into detail, but like is proportional to the security parameter. And our communication complexity in this case, when you instantiate right here, where security parameter is 64, when you instantiate k equal to 1, when you plug this and put it to 1, it's around half the communication complexity of the previous one. So we do have these asymptotic and concrete improvements as well. This is for the offline phase. For the online phase, we have a similar table. Now the communication is linear, we divided by n minus 1. Everything is divided by n minus 1. And again, the main insight here is that we don't need to pay this complexity on the security parameter. Our communication complexity is a constant, smaller constant this time, that does not depend on S. So that's the main insight. And again, it depends. If S is very small, maybe our protocol doesn't benefit you that much. But if your security parameter, a statistical security parameter is large, then yeah, our protocol will provide some benefits. So for S equal to 64, for example, it turns out we can lower the constant from 19 to roughly 12. And in this case, for example, if S is equal to 64 and K is 32, so your computation is over 32-bit integers, we have around the same complexity as speeds to K. But if now you have smaller integers, then our protocol will be almost half the communication complexity of speeds. Again, it depends on the setting. And I want to mention here that for binary computation, you can see that our protocol has a constant, for example, for 64 bits. Our protocol has a constant of 12.4K, which if K is equal to 1, it's just 12.4. Cascudo et al. Is slightly smaller, but as I don't think I will be able to discuss this, but I want to say that our protocol is much simpler and it has fewer rounds. All of them are have rounds proportional to the depth of the circuit, but ours is half the amount of rounds. Okay. So with this, I think it's about time to get to the technical details, at least part of them. So let me start by saying what a Galois ring is. I've been mentioning this for a while, and I think it's useful, of course, to describe it in detail. These have popped up already a lot in other settings, like distributed zero knowledge proofs over the rings. They also appear, these type of ring extensions, or they also appear in the honest majority scenario a lot to instantiate symmetrical sharing. They have different uses. So a Galois ring is nothing more than a generalization of a Galois field extension. So it's a degree D extension of the base ring that we're denoting here by C to the K. And this is going to be the notation I'm going to use onwards, R, for the extension ring, where it's a quotient ring where f of x is a degree D irreducible polynomial over C to the K. It's like a field extension, but like now. So we are the first ones in giving them some use in the dishonest majority setting, as I was mentioning. And the main property of these rings that we care about is the following. So there are many ways of describing this property, but I'm describing it like this. And it says the following: if you give me a uniformly random element in the ring alpha, and you choose whatever you want to choose as long as it's independent of alpha, delta and epsilon in the ring, where delta is non-zero, then the probability that this equation is satisfied is upper bounded by 2 to the minus the degree. D is the degree of the extension. So this way, if you choose the degree of the extension to be 40 bits, like 40, then you can get a statistical security of 40 bits, because this ultimately will be reflected in a statistical security. So that's very good. And indeed, this property, as it stands, as I'm showing it right there, you can just go and pick your favorite field-based protocol and pretty much use this. And this is the property that is underlying all those protocols. It's not even about invertibility of elements, is that this type of equations hold with low probability. And by using this property, you can get MPC over R. If it interests you to use MPC over R for some reason, you can get MPC over R by using this property, following the templates that previous work have done. The template, I'm showing it here at a very high level, is secret sharing an element, but of course, this time you're going to use with max, so you're going to use secret sharing with max. So this is roughly how they look. I'm also making use of this slide to introduce a notation. By the way, this is going to be angled bracket of X is going to be authenticated secret shares of a vector, sorry, not a vector, of a ring element. I think someone unmuted in this one. Okay, so and this is going to be additive secret sharing, the square bracket. So by using this type of secret sharing, you can get additions for free. They're local. You can pre-process Beaver triples or multiplication triples for handling multiplications, which only require openings. You can use the arithmetic, the algebraic manipulation detection code, which is basically this fancier name for this thing I'm just describing here. You can use this for verifying that the openings are done correctly. And this is a template automatically give you MPC over R. But we don't care about MPC over R. We care about MPC over C to the K, which is the base ring. So how do we move from one to the other? So there's a trivial way of doing it, which is if you notice R is an extension ring, which basically elements in R are polynomials of certain bounded degree. So you can obtain MPC over the base ring if you simply consider constant polynomials. Or in other words, a bit more formal, the ring C2 to the K is a sub-ring of R. So if you get MPC over R, you automatically get MPC over C2 to the K. Right? So you can just consider them to be constant polynomials and you can get MPC over R, over C2 to the K. But the problem of this is that this will be wasteful, very wasteful in terms of communication. We don't want this because for every single ring element, you are considering a very large field. For every single base ring element, you're considering a very large polynomial. So to avoid this, RMFs come to the rescue to precisely avoid this type of thing. So what is an RMFE? It's a pair of functions that map vectors of base ring elements to polynomials, so to speak, and another function that maps them back, polynomials to vectors, such that this is the main equation we have to remember. It basically says if you take a vector and map it to a ring element, and you take another vector and map it to a ring element, and you multiply them as ring elements, and you map them back to vectors, you get the component-wise product. This is what this star is denoting. You get the component-wise product of the two vectors. That's what an RMFE is for. And at a high level, what it enables now is that you can do, by using multiplication over R, which is what's happening in here, you can get L simultaneous computations over the base ring. That's what's happening. It's giving you component-wise product or Schur product, which is essentially many parallel computations over L, over C2 to the K. And it turns out that you can choose D to be a constant factor of L. So basically, by encoding a constant factor larger, you take your vector and you encode them in a constant factor larger polynomial element, you can instantiate element-wise computation over the original vector. So this is essentially the tool we use. And if I do want to mention briefly here the way that we encode vectors. I don't think we need to worry so much about the details. I just want to mention that you can use RMFEs with a technique that was proposed one of our papers in Ashpol et al. In AsiaCrypt last year. And that was in the honest majority setting, but here we use it in the dishonest majority scenario. So that's the way you will encode elements. And it turns out that this gives you MPC for parallel executions. The encoding exactly is not relevant for the discussion. I just want to mention that that's what we use. And another fact from that paper, which can be translated to the dishonest majority setting, is that if you have certain quintuples, it's not multiplication triples anymore. It's going to be a much more complex data structure. But if you have certain quintuples, which look like this, so they are A, B, and then you apply this function that turns out to be a mapping that goes from R to R. So if you apply this function to A and this function to B, you're supposed to have sharings of those, and then sharings of the product of these two. If you have a quintuple that looks like this, you can do a secure multiplication in this new encoding or this new parallel computation scenario in just one round, in contrast to previous work that do it in 2 rounds. So just want to highlight this is the way we do it. And it mostly comes from this previous work. So this already kind of gives us MPC if you have these quintuples that I'm not showing how to get. And then we follow the template and we compute the communication complexity that I already described. Okay, so I think I just wanted to, I have some things to show, but like I think it's, the last thing I want to mention is how we get OLE. I'm not mentioning why we need it, but it turns out we need OLE over the extension ring. So in OLE, it's just basically one party has A and B and the other one has X. They are over the extension ring and they want to obtain Y equal to A times X plus B. And I'm going with this, I'm just going to show you the protocol, how we get it. So in the protocol, we use MFEs. It's not an RMFE, it's MFE. So the details of an MFE is this is the equation. It's similar to an RMFE, but this time we map ring elements to vectors, multiply component-wise the vectors, and then map them back to ring multiplication. RMFEs exist, we can construct them, MFEs exist, and so on. And it turns out, this is the main slide. I'm mentioning this because this may be useful in other settings if you're interested in using OLE over extension fields. So anyway, what's happening here is that you're mapping vectors, you're mapping ring elements to vectors, doing OLE over the vectors, mapping them back to ring elements. For the interest of time, I don't think I will be able to continue this, but basically, I didn't plan to present this anyway. So these are some future directions I would like for you to think about. I won't list them, but like you can find the slides online. And with this, I would like to thank you.
All right, for interest of making it to the invited talk in time, unfortunately, there's no time for questions. So let's thank all the speakers in this session.